Swayam Prabha. Digital India. Educated India.
So, in this lecture we continue with our discussion on inter-process communication. So, if you recall, in the last few lectures we discussed the basic problems that may arise when a number of concurrent processes are trying to access some shared resources, particularly the critical section problem, and also we looked at various solutions using which we can try and circumvent them. For example, we looked at various kinds of locks, semaphores, monitors and so on. So, today in this lecture we shall be talking about three classical problems. These three classical problems, actually these are not very specific to operating systems or computer science or any specific field. These are very general problems, and you will see that in this kind of problems the problem of synchronization becomes very important, because there are some very subtle issues where you need to take care and ensure that the solution gives correct behavior. Okay. So, basically what we shall do with the help of these three examples, we shall see how the basic primitives that we talked about for synchronization, specifically semaphore, because semaphore is the most powerful one, we shall be using that as examples, how they can be used to solve these problems. Okay. Fine. So, some classical examples or problems of synchronization. So, here we shall be discussing basically three problems, and as I said, these three problems concern various kinds of synchronization requirements, and the requirements are very different. These three problems are not exactly very similar, but they bring out some issues regarding synchronization requirements that we need to find a solution to. Okay. So, these three problems are, first one is something called bounded buffer producer consumer problem. So, we shall be discussing this in detail, but basically the idea is there is a producer process, there is a consumer process. Producer is producing something, consumer is consuming something, but there is a common shared area. After producing, the producer will be storing some item in that, let us say, buffer, and the consumer will take out the item from the buffer. So, the buffer becomes a shared resource. So, we need to provide synchronization here, and bounded buffer means the size of the buffer is limited. We cannot try and store unlimited number of items in the buffer. If the maximum size of the buffer is 100, we can only store 100 items at a time. Okay. And the second problem is the so called readers writers problem. Well, here again there is the concept of a shared resource. We have a shared resource, there are some reader processes, there are some writer processes, and as the name implies, reader processes are only reading the values of the data items, they are not updating them, and the writer process can additionally write data values into those shared data items. So, here there is a necessity to provide synchronization, how these readers and writers should be synchronized among themselves. Okay. And the third one is an interesting problem. This we shall be discussing when we go to this topic. So, here we shall see that there is a possibility that some of the processes might get stuck indefinitely if we are not careful enough in formulating the solution correctly. Okay. There can be the possibility of something called deadlock. So, this third example brings out the notion of deadlock, and we shall see some of the solutions how we can possibly solve it. Fine. So, we start with the first problem, bounded buffer producer consumer problem. So, essentially we are talking about concurrent processes. So, the problem goes like this: we assume that there are a set of n producer processes, let us call them P1, P2 to Pn. So, what the producer processes are doing? They are producing some item and they are storing it in a buffer. Now, this item can be anything. Okay. Suppose you are reading something from an input device, whenever you read a block of data, that can be your item, you store it in the buffer. You are doing some calculation, some computation. So, whenever one unit of computation is complete, the result needs to be stored somewhere, that is an item. So, the producer process can basically be anything. Okay. Now, in a factory, when you see, there are some machines which are producing some manufactured items, that can also be a producer. Okay. And consumer does the reverse. Consumer is taking the items which were produced and stored in the buffer, it will take them out from the buffer. So, we assume that there are m number of such consumer processes, C1, C2 to Cm. So, on one hand, the producer process will be producing an item first, and then it will be storing it in a buffer. And on the other hand, the consumer process will be removing an item from the buffer first, and then it will be using it, and we are saying it is consuming it. Suppose we are trying to print something. You may be knowing that there is a concept of print spooler. So, whenever the programs are giving something to print, they are stored in a buffer, that is my buffer. So, producer process are the print commands, and there is a print spooler which is running in the background, which is the consumer, which takes out items from the buffer and sends it to the printer. That is how it consumes it. Okay. Now, the restrictions that we impose are, these are realistic. First one is, we assume that the number of items in the buffer is limited, because they are typically stored in memory and you do not have indefinite memory, right. There is some restriction. And suppose at some point in time you are putting the items in the buffer, right. You see that the buffer is already full, there is no free space available. So, now if a producer still wants to produce an item, the producer has to wait, because it cannot put the item in the buffer, it is already full. So, a producer will be waiting if the buffer is full. Similarly, whenever a consumer process is trying to take out some item from the buffer, it will check whether the buffer is empty or not. If it finds that the buffer is empty, there is nothing to consume. So, the consumer process will be waiting, will wait till some item is produced and put in the buffer. Okay. This is the basic problem. Diagrammatically, it can be depicted like this, where we have this buffer which is our shared data item. Buffer is our common shared memory, where all the producer and consumer processes are accessing it. They are updating it. Producer process will be writing into it and consumer process will be removing from it. Okay. So, as I have said, there are n number of producer processes P1, P2 to Pn, and there are n number of consumer processes C1, C2 to Cm. They are all running concurrently. Now, in this solution, we have to determine or say that how this producer and consumer processes must be written, at least the skeleton, so that the access to this common shared memory buffer is correct, there is no race condition, there is no problem anywhere. Okay. Let us see. So, the first thing we talk about is what are the different kinds of data structures and variables that we are using in our solution. First thing, we said that the size of the buffer is limited. We assume that the size is n, which means if I have a buffer, there is space to hold n number of items, maximum storage capacity is n. Okay. And for various kinds of synchronization purposes, we will be using 3 semaphores. Let us also try to understand why you need 3 semaphores. First is, this buffer is a critical section, it is a common shared memory, you are updating some common shared data there. So, all access to the buffer must be treated as a critical section problem. So, the semaphore mutex, this is the short form for mutual exclusion. Mutex is used to provide exclusive access to the critical section. So, among all the producer and consumer processes, at most one can enter the critical section and make some changes in the buffer. So, this mutex acts like a lock. If you recall, a value of 1 indicates it is unlocked, someone can enter, 0 means it is locked, you have to wait, you cannot enter. Okay. And there are two more semaphores, we call it full and empty. Actually, they indicate number of items already in the buffer, full items in the buffer. So, how many items are currently stored in the buffer, that is full, and empty means how many empty spaces are there in the buffer. So, initially the buffer is empty. So, full is initialized to 0, nothing in the buffer, and all the entries are empty, all the n entries. So, empty is initialized to n. Now, whenever a producer deposits an item in the buffer, so what happens? Full will be decremented by 1 and empty will be increased by 1. See, for a producer process, you see, full will be increased by 1, there will be one more filled up element, and number of empty elements in the buffer will get reduced by 1, right. This is for the producer. And for the consumer, similarly, whenever a consumer takes out, so number of full elements in the buffer will be reducing by 1 and the number of empty elements will increase by 1. So, you see this full equal to full plus 1, full equal to full minus 1, this again is a critical section, right. Full and empty are common shared variables which you are updating, one process is incrementing, one process is decrementing. Just to ensure that these operations are atomic, there is no race condition, we define them as general or counting semaphores. So, if you do a wait on full or empty, the value will decrease by 1. If you do a signal on full or empty, the value will increase by 1. This is what we are doing. So, as I said, if the buffer is already full and a producer process is trying to do a signal, it will see that it is already full, there is no further space, or empty, it is trying to decrement, it will have to wait there. So, let us see the solution, we will understand how it works. So, the solution for the producer process goes like this. This is the producer process. So, each producer process will be doing this, it will be running in a loop. So, there will be a loop continuously, it will be doing. So, the producer process is supposed to produce something, right. So, let us say it is producing an item. So, here I am showing it as a function called produce item, and after producing that item, let us say it is storing the item in some variable next prod, right. And after producing, as I said, the number of empty buffers has to decrease by 1, we are decreasing empty by 1. Then the item has to be added to the buffer. Now, buffer is a critical section, so it is protected by mutex. You are doing a wait mutex here, you are doing a signal mutex after that. In between, you are adding the item to the buffer by again making a function called add to buffer, let us say, where you are adding this item next prod. And after you have added, the number of full elements you increase by 1, signal full. So, you see, if the buffer is already full, what the producer process will do? It will get stuck here, wait empty, because if the buffer is already full, the value of empty will be 0, right, empty will be 0 if the buffer is already full, no empty space. So, a wait system call will check it is 0 and it will be waiting, the process will go to the block state, right. So, this way you can ensure that correct access to the buffer is done. Similarly, for the consumer process, for each consumer process the general flow will be this. Again we assume that it is running in a loop. So, consumer process is trying to consume something from the buffer, take out something. So, what it will do? It will first check whether the buffer is full or empty. Wait full means what? If there are some items already in the buffer, full will have a non-zero value. So, wait will be successful, it will go inside. But if full is 0, full 0 means the buffer is empty, there are no full items in the buffer. So, the consumer has to wait. So, it will be waiting in that wait full. Then if it is not, there is some items there, it will take the item out from the buffer. It is doing protected by again this semaphore mutex, where the buffer is a critical section, shared memory. So, it is using wait mutex, signal mutex, and in between it is removing an item from the buffer by making a call to this function remove from buffer. Let us say the item is getting stored in next cons, next consumed, and after you have taken out the item, you increase the number of empty buffers by 1, signal empty, and then whatever consumption you can consume the item after that. So, whatever you do, send it to the printer, whatever you do some processing, whatever the consumer process has to do with that data, it does, and the process repeats. So, you see this mutex ensures that access to the common shared buffer is protected. At most one process can add or remove items from the buffer, and full and mutex, full and empty basically does two things. They keep track of how many full items are there in the buffer, how many items are already there, how many empty places are there. Additionally, it also makes the producer wait if the buffer is full, it makes the consumer wait if the buffer is empty. So, these are the dual purposes of those semaphores. Okay? Fine. Let us now look at the second problem, readers writers problem. This is a different kind of a problem where we assume, well, in the context of operating system I am saying, there are a number of processes which are trying to concurrently update something. It can be a file, it can be a database, it can be anything. Reader processes are only reading the data from the file, not updating. So, you see, if the reader process is only reading, and if there are multiple reader processes that are running concurrently, there can be no critical section problem, because reading is harmless, right? You are not updating anything. So, 2, 3, 4, 10 reader processes, even if they are running concurrently, there is no harm, they are just reading. But there are also writer processes. What the writer process is doing, writer process can do a read as well as it can do a write, which means it is updating the shared variable, and whenever this updation comes in, it becomes a critical section problem. So, the idea is whenever a writer process is writing something, no other process should be able to access the shared data, no reader process, no other writer process. So, writer process should have exclusive access to the shared data item, but multiple readers can have concurrent access, they can access the data items at the same time, no problem there, right. So, here we are assuming that there are n number of reader processes, let us call them R1, R2 to Rn, which are trying to read from some shared data item. There are m number of writer processes W1 to Wm, they are trying to do some updations on the shared data item. So, as I said, the reader process can only read, it does not carry out any kind of write or update, okay. But a writer process can do a read as well as it can do a write. So, it is changing the value of the data item, that is the purpose of the writer process. Okay. Let us see. So, diagrammatically it is depicted like this. So, as I said, you have the common area, this is your shared data set, there are n number of readers on one side which are only reading. So, just note the direction of the arrows, it is only reading the data from the data set, these are the direction of the arrows. And on the other side you have some writer processes which can do a read as well as write, which means these arrows are bidirectional. So, as I had said earlier, any correct solution to this problem should ensure firstly that multiple readers should be able to access the data at any given time, provided there are no active writers. If there are some writers already active, no one can access, right. But if there are no writers, any number of readers can access the data item at any given time, no problem. But as I had said, whenever a writer becomes active, a writer must be given exclusive access to the data item. So, whenever the writer is accessing, no one else should be able to access the data items. No reader, no other writer. It is a pure critical section problem that is coming in, because if you allow another reader to be active concurrently with a writer. So, whenever a writer is updating something, possibly the reader is trying to read that same data item. So, some inconsistent data might be read, right, that may happen. So, to avoid that, writing should be done in an exclusive way, right. This is what our requirement is. So, in this solution also we need some data structures and variables. Well, of course, the common shared data, that is we are calling it data set, that has to be shared by all the reader and writer processes. And in this solution we are using some semaphores and also some shared variables. Two semaphores are used. I mean, we shall understand their use when you see the solution, look at the solution. Two semaphores are used, both of them are binary semaphores. They can have values of zeros and ones. So, first semaphore is read write mutex, another is mutex. Let us see when mutex is used and when RW mutex is used. And because they are binary semaphore, you can understand they are used for some kind of locking and unlocking. In addition, you are maintaining another variable, a shared variable read count, which actually keeps track of how many active readers are there at any given time. This actually gives you how many active readers. So, initially no processor running, so this is initialized to 0. Okay. Now, let us look at the solution. Let us look at the writer process first, because writer is easier, the structure of the process is simpler. See, the writer is very simple. The writer is trying to have access to the shared data, and when it gets access, it must be exclusive, no one else should be able to access. So, you use the read write mutex semaphore to lock the shared data, access it, finish access, unlock it. So, your structure of your writer process, let us say WI, ith writer process, will be something like this. It again runs in a loop, repeatedly it is doing this. It locks using a semaphore wait call, and RW mutex, this semaphore RW mutex, you can now understand, this provides exclusive access to the shared data. Right. So, before trying to use it, it is locking it using wait, then it is actually doing the writing, whatever writing or updation is done required, that code is there in between, and finally after you are done, you are again unlocking it by a signal. So, writer process is very simple. wait, write into it and then do a signal. Okay, fine. Now, the reader process is a little more complex. Let us try to understand the requirement of a reader process. You see, first let us try to understand what are the requirements here. Suppose I am a reader. So, what I should check? First thing is, I should check whether there are any active writers or not. If there are any active writers, I should not proceed, I should wait. Someone is writing into the shared data. So, I have to wait, right. And other thing is that I also here keep count of how many readers are there, because if the number of readers is greater than 0, which means some of the readers are already active. In this period, if some writer is already trying to access, the writer has to wait. So, you look at this previous code, just understand one thing, the writer is entering the critical section by a wait of RW mutex, but suppose one of the reader process is already active. So, if the reader is active, so the requirement is like this, if a reader is active, so you must somehow make the value of RW mutex equal to 0, such that a writer process cannot enter the critical section during that time, as long as some readers are already active. Only when there are no readers, then the writer can enter peacefully, it can have exclusive access. So, now let us try to understand the code. So, how it works? See, there are two parts, one part is here, one part is here. Now, in between you are carrying out the actual reading. In the first part, let us see what you are doing. Here basically you are a reader process, you are first checking using wait mutex. So, what this wait mutex is doing? Wait mutex is a kind of lock. So, wait mutex is telling that when I am doing this, no other reader process should be able to do this. Note, the writer process is not using mutex, it is using RW mutex. Only the reader process is using mutex. So, this wait and the matching signal, it is protecting a critical section which is here. It is updating the value of read count, how many readers are there. That is the critical section in the small part of the code. So, what it is doing? So, I am a reader, I am increasing the reader count by 1 and I am checking after increasing by 1, if the read count is 1, that means am I the first reader? If I am the first reader, then I have to lock access to the shared data, and RW mutex is the semaphore which is providing that lock. So, if I am the first reader, then I am invoking a wait mutex call, wait RW mutex. What does it say? This actually says that if I am the first reader, then I am locking access to the shared data. Now, after me, if any other reader comes, they do not have to lock separately, because it is already locked by me, they can directly access, fine. But if some writer is already active, then the reader process will be blocked in this wait RW mutex. So, it will be waiting here till the writer finishes. Now, after reading is complete, in the second part, let us see what is done here. So, again this is the small critical section part here, which is protected by mutex. So, what you are doing here? Here this reader process is complete. So, the read count is decremented by 1. Now, you check if read count has become 0 or not. 0 means I was the last reader, there is no other reader in the system. So, if read count is 0, it means now I can release my lock on the shared data. Now, any writer, if it wants to, can enter the critical section. So, if read count is 0, I am giving a signal on RW mutex, so that the writer can now go and access the shared data, right. This is how it works. So, the code may be a little big and a little complex, but once you understand the purpose of the different semaphores, it will be fairly easy to interpret how it works, right. Now, in this solution, one thing you note, there is a problem. See, there is a reader process, there is a writer process. Let us say there is a writer process Wi who is trying to enter, but finds that the shared data is already locked by some reader. So, it is waiting. On the other side, there are a number of readers R1, R2 to Rn who are continuously trying to read something in a loop. Continuously means at no time number of readers is becoming 0. Suppose one reader finishes, after another reader joins, another reader finishes, another reader joins. So, all the time at least one reader is active. So, one reader is active means what? The value of RW mutex remains locked. So, this writer is never allowed to proceed further. It will be waiting indefinitely or that wait RW mutex call. So, this is something which is called starvation, problem of starvation. So, if there is a steady stream of readers which are coming, a writer process may starve. It can never get the chance to write into the buffer, because this RW mutex lock, it always remains 0. Only the last, you see the previous code, only the last reader, when read count is 0, then only signal RW mutex is done, not before that. Okay. So, this is the problem. So, of course, several solutions you can think to solve this problem. One solution, I am just mentioning it, I am not showing you the solution. It says that whenever a writer process becomes ready, that it is now ready to write, what I do is that I do not allow any new readers to join the queue. See, earlier the problem was happening because readers were coming continuously, and the first reader was locking RW mutex, and the other readers were using that lock to continue that, extend that lock, extend that lock. But now it is saying that if a writer is waiting, no newly arrived reader will be allowed to proceed. So, the writer has to wait only for a finite time. The readers which are already inside, let them finish, come out, then the writer can enter. And there are several other solutions that are also there. I am not going into these details. Okay. Now, let us look at a very interesting problem, the third problem. This is the so called dining philosopher's problem. Well, I shall be showing this diagrammatically in the next slide, but let me first explain the idea. Let us assume that there are n philosophers sitting in a table. There is a round table, the table is round, there are some chairs placed on the tables, the philosophers are sitting in the table, and in the middle there is a bowl of noodles which is the shared data. The philosophers will pick out some noodles into their plates and they will eat. So, for the n philosophers there are n number of chairs, there are n number of plates on the table, and in between the plates there are some chopsticks which are kept, one chopstick between two plates. So, let us say if there are 5 plates, 1, 2, 3, 4 and 5, there will be one chopstick placed here, one chopstick here, one chopstick here, one chopstick here and one chopstick here. So, there are n plates, there will be n chopsticks. Okay. Now, being a philosopher, you know, philosophers think a lot, they think about almost anything. So, here Our assumption is that a philosopher does two things in their life. They alternate between thinking and eating. Most of the time they think, and whenever they feel hungry, they come to the table and eat. Again they go back and start thinking. So, thinking, eating, that is in a cycle they do indefinitely. Now, there are some protocols they are following. Let us understand what are the protocols. The first protocol is, when a philosopher is eating, what the philosopher will do? There is a bowl of noodle in the middle. With one chopstick they cannot pick, they need two chopsticks. So, the philosopher, I am a philosopher, I will be picking up my right chopstick, I will be picking up my left chopstick, and using the two chopsticks I will pick up noodles from my bowl into my plate, and then I shall start to eat. So, as long as I am eating, I am holding both the chopsticks, left and right. So, you can understand one thing, when I am eating, neither the philosopher on my right or on my left they can eat, because one chopstick I am having with me, they are not having both the chopsticks, right. So, we are assuming when a philosopher starts to eat, they will be picking up the chopsticks. Let us say first it picks up the left chopstick, then it picks up the right chopstick, in that order. First I pick up the left one, then I pick up the right one. And after I have finished my eating, now again I shall be going back to my thinking mode. I place the chopsticks back on the table and then I go back to thinking. And during thinking, I do not grab any chopsticks, the chopsticks are on the table. So, now the others can use them if they want. This is the problem, right. Now, in this problem, let us first look at one solution and then discuss what can be the problem in this solution. Let us see. First let us look into the problem diagrammatically. This is the pictorial depiction. Here, without loss of generality, we are assuming there are 5 philosophers, n equal to 5. So, P1, P2, P3, P4, P5, these are the 5 chairs, the philosophers are sitting on the chairs. Here the plates are not shown, let us say there are 5 plates also kept here, there are 5 plates and the red bars are the chopsticks. In the middle, in this bowl, you have the noodles. So, in this problem, the noodle in the middle, that is my shared data set. All the philosophers have to share that data. That is the critical section problem, right. And there are 5 chopsticks. A chopstick can be grabbed only by one philosopher at a time, right. So, for locking a chopstick, let us say I have a chopstick array, like let us say I have declared semaphore, chopstick 5. So, let us say there will be 5 variables, one is chopstick 1, chopsticks 2 and so on up to chopstick 5. So, for the 5 chopsticks I have declared these 5 semaphore variables and I assume all of them are initialized to 1, means they are unlocked, they are available. So, whenever I want to pick up a semaphore, I have to give a weight on that chopstick, then I can pick up. Okay. Let us see one possible solution now. For a philosopher Pi, this is a solution for philosopher Pi. Now, you think of the problem that I am talking of 5 philosophers P1, P2, P3, P4 and P5. There are 5 philosophers and I am talking about philosopher number I, Pi. I can be anything 1, 2, 3, 4, 5. Suppose let us say I am philosopher number 4, P4, and this numbering I am doing like this. this chopstick I am numbering as 1, this chopstick I am numbering as 2, this one I am numbering as 3, this I am numbering as 4, this one I am numbering as 5. So, if I am philosopher number P4, then I have to pick up chopstick number 4 and chopstick number 5 in that order. So, you see it is doing just that. Philosopher Pi, it is first picking up chopstick I, that is the chopstick on the right in this diagram, and chopstick I plus 1 modulo 5. Modulo 5 means because after 5 again 1 will be coming. So, if it is 4, 4 plus 1 5, okay, like that. So, now after this the philosopher will start eating. Now, after the eating is complete, philosopher will again put back the chopsticks. P4 will put back chopstick 4, then 5. It will put back chopstick I, then I plus 1. Right. Now, try to think what will happen here now. What might happen? Think of a scenario where all the philosophers, they become hungry at the same time. They stop thinking and they go to the table and try to pick up their chopsticks. Now according to this algorithm, philosopher I will first pick up chopstick I and then I plus 1. Suppose everyone picks up chopstick I, P1 picks up chopstick 1, P2 picks up chopstick 2, P3 picks up 3, P4 picks up 4 and P5 picks up 5. And what will happen? I have picked up one chopstick, and when I am trying to pick up the other chopstick, I find that it is not there, someone has already picked up. So, none of the 5 philosophers can proceed. So, this is the problem with this algorithm. So, all the 5 philosophers may want to eat at the same time, and each can pick up one of the chopsticks, let us say I, left or right, whatever you call, that is a convention, and it has picked up one chopsticks and they will never get the other chopsticks, because the person sitting in the neighboring position has already picked that up. Under this situation, none of the philosopher can continue to eat, and they will be in that state indefinitely, no one can proceed and they will starve to death. This is what this problem says, that they will not be able to proceed. This is a classical example of something called deadlock. You see, each philosopher, if you think it as a process is holding a resource, that means one chopstick, that is a resource, and is waiting for some other resource to proceed, but that some other resource is being held by some other process, and there is a cyclic chain. P1 is waiting for P2, P2 is waiting for P3, P3 is waiting for P4, P5 is waiting for P5, P4 is waiting for P5, and P5 back is waiting for P1. So, there is a cyclic waiting chain, and whenever such a waiting chain happens, none of these processes can proceed, and we have something which is called a deadlock scenario. Now, you can think of some solutions by which you can try to circumvent this problem. See, in our next lecture, we shall be talking about some of the actual functions or this kind of locking unlocking functions that are available in Unix or Linux, and we shall show you some sample codes in C or C++, how you can actually do locking unlocking in your code whenever you write it. There you will see that when you use semaphores, there is a facility using which you can do wait or signal on more than one semaphore simultaneously. See here what was happening, here see one philosopher was doing say wait on chopstick 1 and then it was waiting on chopstick 2. Some other philosopher was doing wait on chopstick 2 and then wait on chopstick 3 like this. Okay. The problem was happening is that one wait was successfully executed by everybody, but they were all waiting on the second wait. They picked up one chopstick and while picking up the second chopstick they find it is not there. To avoid that scenario, what you can do? You can have a mechanism where both the chopsticks can be locked at the same time, not one after the other. Now, you will see in Unix there is a facility using which you can lock any number of semaphore variables at a given time in an atomic way. That can solve this problem. So, I am not showing the solution, I am just giving you the idea. So, what you are saying that a philosopher will pick up both the chopsticks only when both are available, otherwise not. If this is ensured, then you can say that at least one of the philosopher will be able to pick up both the chopsticks. He can finish eating and then leave, and once he leaves the chopsticks, some other philosopher can start eating. So, there will be no starvation, no one will be starving indefinitely. So, this is one solution which is feasible, which is possible, which can be implemented in this kind of scenarios. And the second solution which is mentioned here, this is a change in the protocol. Like say I am a philosopher, I am picking up my left chopstick first and then right. My neighbor will be following something different. My neighbor will be picking up the right chopstick first and then the left. So, alternately the philosophers will be following the reverse philosophy. So, you can think that if you follow this reverse philosophy, this deadlock will never happen, because see I am picking up my left and waiting for the right, but my right neighbor is first picking up the right and then picking up the left. So, it will never happen that both of us are waiting indefinitely. Either my right neighbor will get both the chopsticks or I will be able to grab my right chopstick. So, one of us will be able to proceed. So, see any correct solution will put some additional restriction, because here you see solution is correct, first one also solution is correct, but you are putting some additional restriction by which possibly the waiting time will be a little more. Unless you have both the chopsticks, you will have to wait, and left right right left, some of the philosopher may have to wait longer, but what you are ensuring is that the deadlock scenario will never happen, right. This is the beauty of this solution. Now, this brings us to the end of this lecture. Now, in the next lecture we shall be looking at some actual implementation examples. Like as I had said, we shall be seeing how in operating systems like Unix or Linux, these kind of locks that we have talked about, mutex locks, semaphore locks, even in terms of threads, there are some thread mutex locks and other locks available. How these locks can be actually used by a C programmer. Let us say you are a programmer who are writing a program in C where there is some shared memory locations which you want to access, how to do that. So, we shall be looking through some actual program segments which you can run on a machine and you can verify that how these things can be actually done in a program and how you can actually implement them. Now, after these things are over, we shall be looking into the other aspects of processes, how processes are scheduled. Specifically, we shall be going back to this deadlock problem. What are the other general methods using which we can handle deadlocks, how you can avoid this kind of processes from getting stuck. See, deadlocks can happen in many of our real life scenarios, like you just imagine a very narrow bridge on top means on a river or a that is a canal, the bridge is so narrow that only one car can pass at a time. But suppose it may so happen two cars from the two directions have entered the bridge at the same time. So, none of them can proceed, one of them have to back out, right, only then the other can proceed. So, for deadlock scenario, this is the philosophy you have to follow. If some processes are indeed got stuck in a deadlock, one of them has to back out, at least one of them has to back out, so that the others can proceed, and that way you can resolve the deadlock. So, these things we shall be discussing in our next classes. So, with this we come to the end of this lecture. Thank you.